Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 46. And this problem asks us or shows us these three substituted benzene rings, and it asks us 4 questions for each one. So let's start with A. Does a substituent donate or withdraw electron density by the inductive effect? So inductive effect is all about electron density and the electron cloud around your atom. So it's all about which atom is more electronegative. So bromine is more electronegative than carbon and hydrogen. So there's going to be an inductive pull of electron density out of the benzene ring. So there's going to be a withdrawing effect out of the benzene ring for A. Now in this second example is that we have carbon, but then we have nitrogen, which is also more electronegative than carbon. So there's also going to be an inductive pull of electron cloud towards the nitrogen atom and out of the benzene ring. So once again, we're withdrawing electron density out of the ring. Last but not least, we also have these two electronegative atoms being more electronegative than carbon. So we're pulling electron density towards the more electronegative atoms, being these two oxygens. So we're inductively pulling electron density out of the ring. So we're withdrawing electron density out of the benzene ring. In B, it's asking us, does the substituents donate or withdraw electron density by their resonance effect? So resonance effect is about having lone pair electrons and whether or not the lone pair electrons, if you do some resonance structures, will that place a negative charge in the benzene ring or a positive charge in the benzene ring? So let's see what happens. Well, bromine has lone pair electrons, so it can inductively donate to make a double bond here, and then you can form a carbanion in your benzene ring. So if I were to draw that out, we have a carbanion here, and then we have a positively charged bromine here. So this one is actually donates electron density within your benzene ring through the resonance. However, the cyano group here, carbon has no lone pair electrons. So the only lone pair electrons that are adjacent to carbon is this pi bond, which we can bind here, making a bond, you make a bond, you break a bond, and that'll give a bond to nitrogen. So as you see here, that would create a carbocation in your benzene ring. So this is going to withdraw electron density through the resonance effect. Now, in this last example, oxygen has lone pair electrons, so oxygen can make a pi bond here, making a bond. You make a bond, you break a bond. So one of the pi bonds will break to now make a carbanion, similar to in this first example here. So obviously, by having a negative charge in your benzene ring, you're donating electron density into the benzene ring, so it's going to be donating. Now in C, on balance, does the substituent make the benzene ring more or less electron rich than the benzene itself? So C is asking for, on balance, is the inductive effect or the resonance effect more dominating in this example? And more often than not, it's kind of hard to say, but the resonance effect will have more of an implication. But then you also got to consider the stability of your resonance structure. So for example, this bromine having a positive charge, this is so highly unstable. Bromine is a very electronegative atom. It does not like being positively charged. Bromine is happy when it's neutral or when it's negatively charged. Being positively charged is a rare thing for bromine, so this resonance structure most likely will not occur in nature. Nothing is promoting this bromine to become positively charged. So because this bromine resonance with the positively charged bromine resonance is so unstable, it's more likely that the inductive pull of electron density will dominate over this resonance structure. So you're going to make the benzene ring less electron rich than a non-substituted benzene ring alone. Now for this middle example, we have actually two factors that are complementing each other. So we have a synergistic effect of two factors. Inductively, we're pulling electron density out of the benzene ring, and with resonance, we're also pulling electron density out of the benzene ring. So obviously, 1 plus 1 equals a positive number, so we're obviously going to have a lower electron density in this benzene ring than benzene alone. Now, in this example, this is actually kind of a unique example because, yes, we have inductive pull of electrons off of, out of the benzene ring and onto these carbon nuclei. However, through this resonance structure, we're actually forming a molecule that has a benzene ring that has a carb anion shown here. So we have a carb anion with lone pair electrons here, but now we're forming oxygen that now has 3 bonds, so it's going to be positively charged. So one can say, well, you use the argument that a positively charged bromine is not stable, so why would a positively charged oxygen be stable? Well, this positively charged oxygen can move around these pi bonds to now make more resonance structures. And what we know about stability is that the more resonance structures you create, the more stable your molecule will be. So right now, we just formed another resonance structure in which we have a positive and negative charge that are very close to each other. So we have some sort of ionic attraction between these two charges and resonance stabilization because we're forming more resonance structures with this molecule. So this donation of electron density into the benzene ring is actually stabilized by the resonance stabilization of this intermediate structure here. So in this case, the resonance will dominate over the withdrawing effect. So this is actually going to make your benzene ring more electron rich than benzene alone. And now, last but not least, D is asking, does the substituent activate or deactivate the benzene ring in electrophilic aromatic substitution? So in electrophilic aromatic substitution, what we have is a benzene ring that's going to act as our nucleophile, and that's going to attack some sort of electrophile. So what we know about nucleophiles is that they need to be electron rich and they need to also be sometimes basic. But the more important thing is that they need to be electron rich. So obviously, if something is going to make your benzene ring less electron rich than benzene alone, then it's going to deactivate this benzene ring for nucleophilic aromatic substitution. However, if you have a substituent that donates electron density into your benzene ring and makes it more electron rich, well, because it's more electron rich, by definition, it's going to be a stronger nucleophile than benzene alone. So obviously, because we have less electron density in the benzene ring, this is going to be deactivated for electrophilic aromatic substitution. Same with this example. This has less electron density in your benzene ring, so it's going to be less activated for electrophilic aromatic substitution. However, this one, because we have more electron density in the benzene ring through the carbanion formation, by default, this benzene ring is going to be more nucleophilic. Therefore, it's going to be activated for electrophilic aromatic substitution.